Hello guys, today I want to show you our newest update, Visual NAND Reconstructor 6.0. Just recently we have released Visual NAND Reconstructor 5.0 and today it's the next version. It's a really big update, it has a lot of new features and I'm sure you're gonna love it. So let's firstly have a look on new resources as we always add to the new updates. List of these resources is not that big because previous update 5.1 was released just 1 month or 2 months ago, and but still we got something for you here. So it's new XOR keys, new memory chip configurations, ECC and read-retry algorithms. All these resources already available in the database. Also, new pinouts has been found, 2 pinouts for UFD drives and 1 for microSD. That's new resources. And the first feature, big feature I wanted to talk with you about, it's a new SLC protocol for reading Sandisk and Toshiba NAND memories. You know that controllers sometimes write in pseudo SLC mode blocks in devices with MLC memory chips. So memory chip has MLC architecture, device has MLC memory chip, but controller can write in SLC mode some blocks into that memory. In pseudo SLC mode, it's the mode when not all pages are used in the block, but each third page only. This mode is used to increase reliability of writing. So the data that is written in that blocks is more reliable, is more safe. And usually it's a file system metadata or some hot data, some buffer data maybe, and so on. And we could actually extract data even before from that blocks. So we could read it in standard mode in MLC, and it would look like this. 1 page has data, then 2 pages have just FF, and then next page has again data. So we could just cut 2 pages, each 2 pages out of 3, and then somehow process that data. But the problem there was that if we read blocks, pseudo SLC blocks in standard mode, in standard protocol, MLC protocol, then we gonna get a lot of bit errors in that block. And even ECC and read-retry would not fix that errors. And that's why sometimes, for example, last version of file system that is written into pseudo SLC block was not available. Now, with this new protocol, we can actually get this data. So this is how it looks like in with standard protocol. Data looks like this, and ECC map is fully red. And even after read-retry, we can't increase quality. If we will read the same blocks with the new protocol, then we're gonna get from the very beginning normal looking data, so we don't need to cut those FF pages, and quality of the data is much better. You can see that it's all green or light green colors here. So this new mode helps to remove bit errors from pseudo SLC blocks. The problem here is that allocation of those pseudo SLC block is not known for now. We still need to read firstly whole dump in MLC mode, and only then we can read it second time in SLC mode, and like firstly we read it in MLC mode. Then we can see that this block is pseudo SLC next one, and this and that and so on. So we can understand that those blocks we want to get in, so we want to read with a new protocol. Then we read whole dump in with the pseudo SLC mode, and then extract necessary blocks from that second dump and insert it into first dump. So for now it works in let's say manual way. I hope that with the next updates we will automate this procedure, and firstly software will read whole dump in MLC mode. Then when when we will be able to analyze data, when we will be able to see pseudo SLC blocks, we can read only those blocks and insert it into final image. Later I'll show you how to use it, how to use this new feature for now. The next huge thing which we added with this update, it's a support for CBM controllers, Chipsbank controllers. This feature is not released yet. I mean, it's not available for all of you guys with this update, because it's, however, we tested all devices that we have in our lab. We still want to do more tests with the real cases. So we ask you to send requests to our support team if you have CBM controllers, and we will try to solve all your cases personally with these new features. For now, I can say that CBM controllers use totally different algorithm of XOR key generation. It's not a standard way like all other devices have. It's very different. Those controllers generate XOR key based on data which is written into in some particular block. One user data will generate one XOR key, another user data may produce another XOR key, yes. And it's we call it adaptive XOR algorithm. And a long time we couldn't extract, we couldn't un-XOR it, descramble it. Now it's possible to do. We tried this approach with very different controllers with different names like CBM 20. Well, actually, you can see the list here of those controllers with the different prefixes. And with all of them, we could descramble data, and the result was good. Another cool thing that we found translation algorithm for Chipsbank, and we may assemble logical images based not on logical block numbers, but on translation table of those devices. So the result of recovery for these controllers is pretty perfect for now. And it's, as I said, it's still on alpha testing. I believe that in next update we will finish it and it will be released for everybody. And now I would like to show you a case with this controller and pseudo SLC reading. So that's the case with the Chipsbank controllers. As you can see, we have two physical images here. One was read with a standard mode of reading, and second one is pseudo SLC. So here we have normal data. Here we have most of blocks damaged or look like it's like this. It's kind of like a garbage. But if we will scroll it from time to time, we'll see blocks that look normally. Oh, I have an idea. I can actually open both these dumps together and scroll it now. And let me find some block. No, it's not going to work like this. I need to open this and this, because in a pseudo SLC mode, each block has size 3 times smaller, because we read each third page. So the total size will be 3 times smaller. So that's why after we got this dump, we need to add the, actually I can do it here on BCR. We need to add the additional FF bytes to each blocks to make a size of result size of these blocks equal to the original one. And now if I will open it, I should be able to see. So this is data that we get from normal blocks in pseudo SLC mode. And you can see that it looks like a garbage. And these FFs we added artificially to make block sizes identical. And now I want to find some blocks with which are written in pseudo SLC mode. Oh, it looks like I got something here. Okay, guys, finally I found one place where we can see from the left side, on the left side, pseudo SLC blocks, how they look like in with the standard protocol, and how they look like in a correct, let's say, protocol for these blocks. Here we have no data, normal data, and from the right side, it's normal looking data. After we descramble it, probably there will be some file system, and even though it's not a lot of data here in this particular block, but this data could be very important for file system. So that's how it works here. And then so this is pseudo SLC thing, and then we just repeat all the steps of preparations for MLC blocks and for pseudo SLC blocks. Then we unite them together, and as a last step we will create. By the way, I forgot to mention that here we have that new element CBM XOR, which will descramble data for us. After data was descrambled, we use standard pair, unite, and as a last step, we need to create translation table. All settings for translation table already pre-installed. So for now, we just need to click on those two buttons and wait a little. Okay, translation table is created, and now let's try to open file system viewer. The thing is that file system here starts not from the very beginning, but with some offset, some shift. So it also takes some time to find the start of file system, but then I hope that we will get it. And it's here. File system is found, and we can see that all pictures, all folders have green flags. And that means that headers are good, and we can actually open pictures. Pictures are good too. So here we have some nice jumping dog. Okay, that's what we do with the CBM controller. XOR transformation and translation table. One more time, guys, these features are not available now for everybody. We are still testing them. If you have some CBM controllers, drop us messages. We will try to solve it personally for you. Okay, the next feature that we added, it's IS XOR. It's a tool for generation of XOR keys for Innostor controllers. You may remember that in the Visual NAND Reconstructor 5.0, we released a tool for XOR key generation for some controllers. Now we continue this tradition. It's a turn of Innostor controllers. I'd like to remind you that this tool doesn't extract XOR key from the dump, but based on data in the dump, it generates XOR key on fly. So it analyzes data, searches for some things, and then based on the things found in dumps, it will generate the key. And if you see something like this, nice green map, so that means that a key is generated. It doesn't have much buttons or options you need to apply. Usually you need just to click on generate XOR key. It will take some time. And after you get such a beautiful green map, you need to click on apply XOR key. So for now, XOR keys of Innostor controllers is not a problem for you anymore. Let's see how it works with a real case. Okay, so that's the case, quite a standard one. 2 crystals ECC, which is already fixed, and the Innostor controller, Innostor XOR key. Let me check how much time it will take for generation. So this is what you actually have to do when you work with such cases normally. You just drop Innostor XOR element on the workspace and click on run. You need to make sure that XOR key size is a correct one. XOR structure is too, but you know, these things are automatically applied. Usually you don't have to worry about them. You just click on run. And wait. Okay, the XOR key is generated. And the last thing we need to do here, we click on apply XOR, and it's here. So actually I can remove this to previous keys, and then I may click on this copy button, so it will create same element, the same key inside, and then I will open markers table for this case and create logical image. And again, all the data is here. And we can just start copying data. So that's Innostor XOR. Works very efficiently and much easier now to descramble cases with this controller. And the next thing of this video, of this presentation, it's actually the main thing of this update. It's a file assembler. This file assembler, as its name suggests, assemble files. That's the main window of the file assembler. We will discuss its options a little bit later. Now let's have a look on files, on supported files by the assembler. For now, we decided to add support for most often asked files from our clients. It's Office files, PDF files, pictures, JPEG pictures and RAW pictures, and video files, MP4 and MOV files. That's the actual list of supported files. If you guys have some files you want to be able to recover and we don't have it here, you can write it in comments or drop us message. We will try to add support for those files. And now several words about this file assembler, how it works actually. And the main thing here I wanted to tell you that it's not yet another virtual translator that assembles files and dumps based on file system metadata. It's all new system that combines three technologies, that uses three technologies in order to bring you files and sometimes original file system. The first technology, it's let's say standard file system metadata and file parameters analysis with some advanced approaches that we added. So yes, that's the first technology. The next one, it's a zip archive elements assembling. So our algorithm analyzes all zip files internals which were found in the dump, and then it's trying to combine whole zip files from those parts. And the last thing, most advanced, most powerful, it's intelligent visual content analysis of multimedia files. I'll tell you about this thing in a while. Firstly, let's see what exactly do we do on file system metadata and file parameters advanced analysis step. So basically, our algorithm scans whole dump and it's trying to search for files and detect file parameters such as size and so on. And also it's searching for file system metadata remains. File system metadata remains may have records about, again, files with its parameters and offsets on disk. So once some particular file with particular parameter was found, then algorithm is looking if there is such a if there is a record for this particular file in file system metadata, and if there is a match here. If system is sure that that record from file system metadata corresponds to some specific file found there, then the system will know like a real logical offset of the found file. So the system will know where this file should be, where this block should be placed in the result image. And that's what it does for all the matches, all the files and file parameters and the file records which are found in file system metadata. And that's the very first step what we do on on this assembling. Then we can perform archive file internal structure analysis. You may know that modern Office applications such as Microsoft Office and OpenOffice, they use in fact zip files for their data. For example, docx file is zip archive with some XML files inside. And that's why this approach is very useful when you recover Office files. And on this step, algorithm scans whole dump and looking for files that belong to zip archives. On this picture, you can see typical structure of a zip file. There is a internal file. What is archive file? It's actually a set of internal files, compressed files all together, and at the end of that file we have a central directory where all allocation of internal files is described. And the system, our algorithm, is looking for internal files of zip archives with its parameters and central directories with parameters. And once some match is found, that, for example, and for some particular central directory, firstly we have this file, then this file and this file, then utility can generate zip file, recreate zip file from that particles, from that parts which could be found across the hard drive, across the flash drive, across the dump. So this approach is kind of similar to the first step, but it's working for zip files, only on zip files level. And the last and most advanced analysis that we can perform here, it's an intelligent visual content analysis. The thing is that on this step, our algorithm is looking for all pictures that are found within the dump. And pictures could be fragmented. One picture, for example, this nice lady, start of this picture we have in this block, and end of the picture we have in another block. So once algorithm found this start of this picture, it's trying kind of analyze visual content, the picture which we have, image that we have actually there. And when this picture ends, we see that another lady starts here in the next block. So algorithm understands, algorithm understands that that's another picture starts here, and so this block shouldn't go after the previous one. And algorithm is looking for preceding of this picture within whole dump. And then when this second part of the picture is found, it will just take this block and connect it to this block. So in other words, it's like algorithm is looking for each and every picture fragment on the dump, and then it's trying to create, to assemble puzzle from all those pictures into picture fragments into good, nice whole pictures, big pictures. And that's a unique thing. It really helps to assemble files on fragmented devices when we can't arrange blocks by LBN. This table shows which files we assemble with which algorithms. So file system metadata scan can recover pictures, zip files, and PDF files. Zip files can recover zip files and Office files, and visual content analysis is used for pictures, raw pictures, and video files. The assembler can work in two modes. First mode, and let's say main mode of work, it's a mode for mixed blocks. So if you could apply ECC for the dump, XOR, and so on and so on. So dump is actually prepared, but blocks are still mixed. You can't assemble blocks. Then you can run this mode, and the algorithm will try to reassemble blocks in logical order. And this mode could be useful for cases such as Toshiba controllers, SSS controllers. So for those devices where we don't have logical block number. Some time ago, we couldn't do a lot with such devices because of that mix. I mean, some pictures could be recovered, which are located within one block. But if a picture is bigger than one block, if we're dealing with a video, then we could do nothing. So now with this assembler, we can deal with Toshiba and SSS controllers or another controller without LBN quite efficiently. And the second mode of work, it's a mode for arranged blocks. And with this mode, assembler works on cluster level. So it's trying to assemble files by clusters. And this mode is efficient for example, formatted memory cards from video cameras. We had many cases when memory card is actually good. It was accidentally formatted in a video camera. And then if we try to analyze this card via standard interface, via SD interface, for example, we can see only zeros here, there. So, but those zeros, it's artificial zeros, which a controller just generates for us. In fact, NAND memory may still have all the data, all the videos there, and we can actually recreate the dump, but due to video files fragmentation, result of recovery was not that good because video files was fragmented, and no one software, logical recovery software, could recover data from that devices. Pictures we could recover, but video files we could not. So again, this assembler can do the job very good. We actually had a case, and I will show you this case later, when we received such a device from formatted camera, and within 1 year we couldn't do anything with this case. We tried, I believe, every available logical recovery software, and it didn't show good any software no one software showed good result because of files were fragmented. Then finally we tried assembler, and all videos were recovered. On this slide we can see assembling options. So it's like scans which you can run. The first scan, it's a basic scan. You can't disable it. I mean, all of those scans are switchable. You can either enable it or disable, but basic scan you can't. And disable, it's a default scan or initial scan. On this scanning, we gather file system metadata, information, some files information, and try to recreate file system and assemble files based on that file system metadata. Sometimes it could be quite efficient, sometimes not, but we decided to use this standard approach in addition to our main approach, flagship approach, video and picture assembling. Then another option is a zip analysis. On that step, fragmented zip files could be assembled by blocks. Then we have two modes for pictures. The first one is assembling pictures by blocks. And if you want to get more pictures, if you believe that not all pictures are recovered, then you can run assembling pictures by clusters. So this mode could be used for good devices. I mean, for devices where you could arrange blocks by LBN, but you believe that there are a lot of fragmented pictures there. However, it's not really regular case. Usually cameras don't fragment pictures a lot when pictures are written into memory cards. Video files, it's another story, but pictures usually are written sequentially. So usually you will need to use these two modes for devices with mixed blocks. And the last mode here, it's the video assembling by frames. So this scan is used for assembling video files by frames. Algorithm is looking for all frames from the dump, and then it's trying to rebuild good videos from that frames. I mentioned before that beside files, this file assembler can actually tries always to recreate file system, and sometimes with some specific set of files, if you will be lucky enough, file system will be original file system will be recovered. To get good file system, the device should have many not that big files. Ideally, that each block will have some unique files, and the file system metadata also should have records about that files. And in that case, file system assembler will be able to recreate original structure and will place the first sector block with a boot sector on the first position, then block with path tables, path folders on the second position, and so on and so on. So sometimes, if some requirements will be done and you will get enough luck, file system will be recovered too. However, the main result, I believe, of our file assembler is files itself. For now, these file systems are supported for recreation. It's FAT 1632, exFAT, and NTFS. And finally, let me say that what you will get after assembler finishes the work. Firstly, of course, you will get files, a list of files, like Explorer with all files there. Then it will create one XML file with assembler results. So it's like a save file, which you can later upload into assembler and get the same results like you got after the scan finish. So for example, you run the scan, it may take a while, then you had to reboot or close task. You can open the task and upload those scan results and proceed to save files. And the last thing, it's assembler block table. So this is XML file which you can try to upload into markers table and get original file system of the case. I will show you how to do this in a minute. Basically, I said everything I wanted to tell you, and now we can check several cases here. So the first case, it's our standard case with aquarium, and we have file system here with all of those pictures, and just to compare results, I ran carving on logical image, and have a look after carver. After the end of carving, I have here 343 good pictures, right? And now let's see how many pictures we will get with our assembler. To run assembler, we need to connect data area element, in this case to the pair. So we need to connect data area instead of these two elements, logical image and markers table. Should look like this. And then we can run file assembler on the data area. This is what you're gonna get, such a window. We tried to do interface quite intuitive. So all the parameters should be easy for understanding, I hope. Here we can switch mode of work, mixed blocks or arranged blocks. In case of you switch to arranged blocks, you set area for scanning. In case of mixed blocks, you need to set up size of block without service area and with service area. Normally, if you have a structure, if you connect it to the chain of solution, those numbers will be taken automatically. If you want to run file assembler on some image, then you will need to set up these numbers manually. Then you should select here file system. If you don't know what file system was there, then you leave unknown. If you know for sure that file system was FAT 16, for example, and then you select it. It will help to algorithm to exclude another file systems which may be located there. For example, some time ago, device had exFAT, last file system is FAT32. So to exclude from analysis exFAT metadata, we select FAT32. And then this metadata will not have any influence on the final results. Then here we can select which what do we want to assemble. Either we want to assemble videos or zip files or whatever, and then we can just run the process: start, pause, and stop. If we have saved results, we can load them. Let me do this. So yes, it's assembler results, and that's what we get here. So have a look on the logical image. On the logical image, we have 343 good pictures. So it's like on ideal image, we have this number of pictures, 300 and half, let's say. On totally mixed image, we have actually the same number, or even one more, plus one more number of pictures. 30 pictures unfragmented and 314 pictures fragmented. But all of them are good. If we try to run file carver on the data area, it will show us much worse result. Okay, guys, and the carving is finished, and now we can compare results between what we can get on mixed dump, and we can see that it's only 29 pictures are good here, and 300 are damaged. And I'd like to remind you that with the assembler, we got 344 pictures actually. So the result is much better. That's the first case I wanted to show you. The next one would be this one, and this is actually a Toshiba case. So the case when we don't have logical block numbers in service area. So we can't build a logical image, but we can apply XOR, we can apply ECC, and on this step we don't have any data transformation, but all blocks are mixed. If we try to run carver on this element, we're gonna get something like this. Let's have a look on JPEG pictures. It's 190 good pictures, and basically that's it. So approximately 200 pictures we could recover. We can recover with a standard approach, with the carving on mixed images, on mixed blocks. Let's see what can we get with the assembler. So I run assembler on the data area, and then upload previously saved results, because analysis will take a long time. And that's what we can get from this device. Here we can see actually all files that are supported for now for recovery. So firstly, it's PDF files, then Office files from OpenOffice, then Office files from Microsoft Office, JPEG pictures, and RAW pictures, and MP4 files, video files. So let's compare JPEG pictures. We could get actually here one picture is unfragmented and 282 pictures are fragmented. So in total we have 283 pictures And with a mixed image, well, actually here we have two mixed image. With a Carvin, we got 190 pictures. So with assembler, we got 100 more pictures, JPEG pictures. And moreover, yes, it takes some time to draw the picture, to render the picture. And yeah, that's it. Also, we got here raw pictures from Nikon camera, raw pictures from Canon camera, and some video files. Let's see what we get here. It's there could be some lags, but in general, it's okay. It's good. Some soldering video and so on. So with the assembler on Toshiba cases, we can get much better results than with a classic approach. And this is what we do and how we do on mixed images. In the next case, I'd like to show you how it can recover fragmented video files. So that's the case from a video camera where memory card was fragmented, and we could reconstruct image quite good. Actually, it's perfectly reconstructed. We have even new file system, which is actually empty because it's new. And the bad thing that we could not get a previous file system. All previous file system metadata was damaged, and with any software which is available now on market, we could not we could not recover those video files. But when we tried this with assembler, have a look. We got 300. We got 12 unfragmented videos, and that's the same videos we could get with another logical recovery software, and 350 videos, fragmented videos, and they are recovered with a really good quality. And even such a big videos we can see, for example, yeah, like this one. You see it's some Indian wedding, and we don't have any artifacts here. Sound is good, and it's perfectly recovered with a very good quality. So for fragmented videos, it's also very useful. And the last case for today, it's this one. Where is that? So here, I wanted to show you how you can upload how you can try to recreate file system. So same story here. We have a logical image. We could recreate logical image here. Just let's compare what results we can get with the Carvin Con ideal image. It's approximately 2000 of pictures, 1900s. Okay, let's run file assembler on data area element, so on mixed blocks. And let me load assembler results, this one. And we have 800 pictures unfragmented, 5 pictures which consist of 2 fragments, and 1000 pictures that are combined from more than 2 fragments. And the same number, have a look, approximately 19 hundreds of pictures are recovered. And let me open some fragmented pictures. You can see that all of them are quite good. If we try to run Carver on data area element, you see data area 0, this element, and then we're gonna get only 700 of good pictures, only 700, so 2 times less, and a lot of damaged pictures, a lot of fragmented pictures. So in this case, result with assembler even more than 2 times better. And moreover, with this case, we can, in case if we would not be able to build logical image with a standard approach, we can use block table, which is made with the assembler. So I can open markers table element and load this assembler block table. So that's the block table which is made by assembler. So there is a list of blocks now, and if I click on create logical image, yeah, I should have now file system on logical image element. Okay, and as you can see, I have it. Let's just open file system here and there and compare them. So this is a file system which is created by assembler, and this is original file system. Original file system is all green. It's quite good. Virtual file system, in this folder, half of pictures have red flags, half of pictures have green flags. But for example, in this picture, in this folder, all pictures are green, and the same like here. So you can see that we have here same names, and basically original file system is recreated from the remains of file system metadata by the assembler. That's what our new product, our new tool can do, our new update. I hope that you enjoyed with this video. Please leave your feedbacks in comments, or you can send it to us. You can write about your experience to us with the assembler. You can ask us about new files which you want, file formats which you want to add for support list. We will process all your requests. For now, it's everything. Thank you very much for watching this video, and I'll see you soon. Bye.